Yes, welcome you all for another session on free vibrations, which are undamped and single degree freedom systems. Probably I shall make today's class as the last class for the discussion of this kind. In fact, when I used to teach vibrations, I used to take 20-25 hours only on this kind of topic, covering wide variety of systems. But anyway, since this is not a vibration full subject and only one module what we are studying, and therefore I shall restrict myself because I can't afford so much time. So now I have another problem. So this is the problem. So here you see so many springs here. See, in fact, I have numbered it. In the question paper it is not numbered. I have numbered them. 1, 2, 3, 4, 5, 6, 7. There are 7 springs and 1 mass. Okay, still it is a single degree freedom system. So here I have springs which are arranged in different manner. Okay, so when you have a combination of springs, the springs may be arranged in 2 possible ways. One is what is called as a springs in series, the other one is called as a springs in parallel. For example, if I take the spring number 1 and 2, 1 and 2, I call them as springs which are in parallel. Okay, then I shall tell you what you mean by series. If I have this kind of arrangement, okay, so springs may be arranged when you have a number of them in 2 combinations. One is called as a series combination, the other one is called as parallel combination. So in this case, what I have is, it is a case of series and parallel. These 2 are parallel. Then the resultant, or what we call it as equivalent spring and the spring they are in series, etc. I shall show you. Okay, what do you mean by springs in series? So if I have a springs, okay, 3 springs. So this is 1, whose stiffness is say K1. Then I have another spring, say this is K2, and say I may have any number, then I am restricting it to 3 springs, say K3. So I say that 3 springs K1, K2, K3 are in series. Okay, so now the same thing can also be considered as an equivalent stiffness. Okay, so I have only one, and this I shall call it as stiffness K equivalent. This is one system in which you have 3 springs which are arranged in series. This is another system which is having only 1 spring. These 2 systems are said to be equivalent when, if both the systems are subjected to the same force and they undergo the same amount of deflection. Okay, the extension of this system and the extension of this system, if they are same, when we apply the same force, then the 2 systems are said to be equivalent to one another. Okay, so now I apply a force here, and here also I apply a force here. Okay, I shall find out what is this, okay, delta. I shall call this as delta equivalent. Okay, what will be delta equivalent? The force F divided by K equivalent. Okay, so here the force, though it is being acting at this end, the end, one end is fixed, the other end is free. Now you know that this force is acting on not only on K3, it is also acting on K2, it is acting on K1. All of them are subjected to the same force. So therefore, delta of this, the total delta, is nothing but delta of 1 plus delta of 2 plus delta of 3. The extension of this spring plus the extension of this spring plus the extension of this spring is the total extension. That's what I have written. This is nothing but, what is the delta 1? This is nothing but F divided by K1. Because this spring is also subjected to F, plus F divided by K2 plus F divided by K3. This is the total extension of the spring, and this is the extension of this system. Okay, now I want to say that these are equivalent to one another. When do you say that they are equivalent to one another? F divided by the extension of this and the extension of this must be equal. F divided by equivalent is equal to F divided by K1 plus F divided by K2 plus F divided by K3. So you can cancel F. This is equal to 1 divided by K equivalent is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3 and so on any number. If you have only 2 springs, then these 2 terms. If you have 3, then if you have 4, like that. That's all. This is what we call it as the equivalent stiffness of springs which are in series. I hope you understand this. This we are going to use while solving that problem. So the equivalent stiffness of the springs which are in series is given by this. Okay, now I have, as you can understand here, okay, this is one spring, this is K1, let me call it, and say I have another spring whose stiffness is K2, and now I am going to apply, see the spring arrangement is like this. So here I have a horizontal line or something rigid bar like that. Okay, this spring and this spring, they are what is called as parallel. The 2 springs are said to be parallel. So now I have another system in which I have only one spring and this is K equivalent. So this is one arrangement, this is another arrangement, and I say that these 2 are equivalent to one another. When I apply the same force here and here, if I find the same extension here and here, then I say that the 2 systems are equivalent to one another. I don't have a separate definition of equivalence. The same thing here. When we apply, okay, if we have 2 systems of springs, okay, so apply for both systems the same amount of force. And if you find the same amount of extension, then we say that they are equivalent to one another. Okay, similarly here, I apply a force F, and here also I apply a force F. Okay, so when I apply a force F, then what is the equivalent? What is this delta equivalent is equal to F divided by K equivalent. Or in other words, F is equal to delta equivalent multiplied by K equivalent. So, here I am applying a force here. I am applying a force here, and this force is being shared by the 2 springs. So please understand the difference between this and this. When the springs are in series, all the springs are subjected to the same amount of force. But here, the load that I apply, so this F is being shared by this and also this. And then I want to make sure that this is always horizontal. So when it is extending, it is going to come something like this. The load F is not shared equally by the 2 springs. If they shared equally, then the extension of this spring is not going to be equal, and in that case, this may become something like this, inclined, depending upon. So here there is a condition that both springs have to undergo the same amount of extension. This force is shared by the spring, and this force is also shared by the spring. If I call, say, F1 and F2, F1, F2 are forces. Forces in what? Forces in K1, that means in spring 1, and K2. Please remember, K1 and K2 are the names of these 2 springs. Okay, so now both undergo, both K1 and K2 undergo what? Same extension. Say delta. Yes, that is delta. So therefore, what is F1? F1 is equal to K1 into delta. And what is F2? F2 is equal to K2 into delta. And what is F? F is equal to F1 plus F2. What is F1? K1 into delta. Delta I shall take it common. And what is F2? F2 is equal to K2 into delta. Okay? When I apply F and F here, this delta and this delta equivalent, they are equal. So therefore I can say that these two are equivalent to one another. Okay, let me assume that is F is equal to F1 plus F2. F is equal to F1 plus F2. What is F? What is F? F is equal to delta equivalent multiplied by K equivalent. And what is F1? F1 is K1 plus K2 multiplied by delta. If delta equivalent is equal to delta, in that case K equivalent is equal to K1 plus K2. That means if the springs are in parallel, then their equivalent stiffness is the sum of the stiffness of all those springs. If I have only two, then it is the sum of two. If I have three like this, one and say second one, third one, I have like this. Then it is K1 plus K2 plus K3. So like that. So if the springs are in parallel, their equivalent stiffness is the sum of the stiffness. If the springs are in series, then the equivalent stiffness is given by this kind. 1 upon equivalent stiffness is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3, like that. So now we shall make use of this and then we shall solve the problem. Okay? So I shall go on simplifying it. So first I shall find out. So do you agree that 1 and 2 are parallel? Okay? So 1 and 2. So 1 and 2, I shall replace it. Replace. Okay? That is K1 and K2, which are parallel. Replaced by what is called as K12. We shall call it as K12. So as we know that 1 and 2 are parallel, so what is the equivalent to stiffness for parallel? K12 is equal to K1 plus K2. I hope you did. Okay, K12. So I shall call it as K now only. K1 is K. I shall substitute it later. K1 is K. And what is K2? K2. That is also K. So therefore, K12 is 2 times. So what I mean is, okay, so this and this can be replaced by only one spring, and whose stiffness is K12. I hope you understand. So that I shall do it here. I hope you have this diagram, original diagram. I am going to modify this. So I am going to replace these two. By what? Only one spring. And what is that? So I am replacing it. So now this is K12. So what is K12? K12 is 2K. Okay. So now K12, this K12. This is K12 and K3. What kind of arrangement? K12 and K3. This is third spring. They are in series. So I would like to find out. So the equivalent stiffness of this 1, 2 and 3, and I call it as 1 upon K1, 2, 3. I would like to replace the springs 1, 2 and 3. So K1, 2, 3 is equal to 1 upon K12, that is one string, and plus 1 upon K3. Okay, let me find out what is 1 upon K12. K12, I know that it is 1 upon 2K plus 1 upon K3. K3 is what? K3 is K only. That is 1 upon K. So simplify this. This is 2K is LCM. This is 1 plus 2. This is nothing but 3 by 2K. Please remember what is the left hand side? It is 1 upon K1, 2, 3. It is not K1, 2, 3. So this is therefore K1, 2, 3. This is 1 upon this. That is reciprocal. So this also, this is equal to 2K divided by 3. 2K divided by 3. That means the springs 1, 2 and 3 can be replaced by only one spring. So I shall replace all this by only one spring. What is that? So this is K1, 2, 3. Okay. In order to save my board, I am using it here only, but I wish you to do it in a new diagram. Don't do it in the same diagram. So 1 upon K1, 2, 3. Now again come back here, observe. So do you agree that K1, 2, 3 and K4, what are they? K1, 2, 3 and K4, they are parallel. Okay. So their equivalent stiffness, I shall call it as K1, 2, 3, 4. So they are parallel and therefore their sum is the equivalent stiffness K1, 2, 3, 4 is equal to what? Sum of stiffnesses of the individuals K1, 2, 3 plus K4. K1, 2, 3 plus K4. What is K1, 2, 3? K1, 2, 3 is 2K divided by 3. And what is K4? That is nothing but K. So simplify this. This is equal to 3 as it is. 2 plus 3. This is 5K divided by 3. Bring it in one stroke. So therefore K1, 2, 3, 4 is 5K by 3. So I can replace 1, 2, 3 and 4. So and call the stiffness 1, 2, 3, 4. That is nothing but this arrangement. I am replacing it by one spring. One spring. What is that? K1, 2, 3, 4. K1, 2, 3, 4. And what is the stiffness of that? It is 5K by 3. Okay, so now I can run this portion. So now this spring and this spring, K1, 2, 3, 4 and 6. I can't jump to 5 because there are two springs which are in series. First I have to find out this and then go here. Okay, 1, 2, 3, 4. Because the numbering I have done it randomly, I have done. Therefore, 1, 2, 3, 4 and 6 I have to take. So 1, 2, 3, 4 and 6 together. All of them. What kind of arrangement? They are in series. So this spring and this spring, they are in series. Their equivalent 1 upon K, 1, 2, 3, 4 and 6. 1, 2, 3, 4, 6. This is equal to 1 upon what? K, 1, 2, 3, 4 plus 1 upon K, 6. Okay. So what is this is equal to? Let me substitute 1 upon K, 1, 2, 3, 4. 1 upon K, 1, 2, 3, 4 is 5K by 3. 5K is here divided by 3. That 3 will go to the numerator. Plus K6. K6 is also equal to K. So this is equal to, simplify this. This is 5K. This is 3 plus 5. This is nothing but 8. 3 here as it is 5. 3 plus 5, 8. Therefore, what is this? This is K, 1, 2, 3, 4, 6 is equal to 5K divided by 8. Very important. So therefore, I can replace 1, 2, 3, 4 and 6. So I shall replace this by only one spring. Only one spring. And what is that? That is K, 1, 2, 3, 4, 6. Okay. So now this and this combination. 1, 2, 3, 4, 6 and 5. What kind of arrangement? They are in parallel. the two springs are in parallel. One spring is 1, 2, 3, 4, 6. The other spring is 5. So therefore, so I shall call it as K equivalent of what? 1, 2, 3, 4, 6 and 5. So I shall call it as K 1, 2, 3, 4, 6, 5. This is equal to, what is that? K 1, 2, 3, 4, 6 plus K of 5. The spring 5. Okay, this is equal to K 1, 2, 3, 4, 6 is 5K divided by 8. And K5 is K. So this is equal to 8 as LCM. This is 5K first term plus 8K. 5K plus 8K is 13K. So 13K divided by 8. So 13K divided by 8 is the equivalent stiffness of 1, 2, 3, 4, 6 and 5. So therefore I can replace this and also this by only one spring whose stiffness is, equivalent stiffness is, what is that? K, this is 1, 2, 3, 4, 6 and 5. Okay, so now, so again I have two springs. So I have two springs now which are in series. So now this is one spring, 1, 2, 3, 4, 6, 5 and 7. So these two are in series. I shall call it as K 1 upon K equivalent. What? 1, 2, 3, 4, 6, 5 and 7. So this is equal to the sum of 1 upon K. What is that? 1, 2, 3, 4, 6, 5 plus 1 upon K 7. K 7 is what? K 7. The stiffness of 7 spring is K. So substitute this now. K7 I shall write it, and maybe in the next step I shall substitute. So this is what? This is 13K, that is, sorry, this is 1 divided by 13K upon 8. So this becomes 8 plus 1 upon K7 is K only. So therefore this is equal to, the LCM is 13K. Okay, this is 13K, that means 8 plus 13, this is 21. So therefore, what? K 1, 2, 3, 4, 6, 5, 7 is what? This is equal to 13K divided by 21. Okay, now these two springs can be replaced by only one spring. So what is that? So that is K 1, 2, 3, 4, 6, 5, 7. So how much is stiffness of this? The stiffness of this is 13K divided by 21. 13K divided. So I have one spring whose stiffness is so much, and this is the mass. So I know that, and what is the natural frequency of a spring mass system? Omega n is equal to square root of K upon m. So many radians per second. Okay, let me substitute. What is K here? What is K? K is 13K divided by 21. 13K divided by 21 divided by m. Okay, so this is equal to square root of 13, and K is what? 2 into 10 raised to 5. 2 into 10 raised to 5 Newton per meter divided by 21 into mass. What is m? M is 20. This is 20 kg. Okay, so simplify this, whatever the answer you get, that is the frequency, natural frequency, and so many radians per second. I hope you have understood. So we solved this problem, but my aim was not only to solve that problem. I also wanted you to understand the combination of springs in series, springs in parallel, and then how to find out the natural frequency of that, etc. All that I wanted to find out. Okay, so the next one. So this kind of the spring combination you may have in many things, very possible ways. Okay. Suppose you have like this, say one arrangement. Say this is K1, and say you have a mass here, and say this is K2. K1 and K2. Okay. So this we also say that the two springs K1 and K2, are they in series or are they in parallel? Okay. So in between you don't have continuous arrangement, you have a mass there. Please understand. Mass is there. Okay. It looks that the springs are in series. They are not. Actually the springs are in parallel. Okay. So no problem. Let me assume that this is the equilibrium position. Anyway, the forces in the springs, whatever are there at the time of equilibrium, they are not going to be there in the final expression of the natural frequency. You might have observed in all the cases so far. So the springs deflection at equilibrium, we call it as delta ST. So did you have delta ST finally in the expression? You don't have. So for example, here also, this mass, okay, if I draw the free body diagram of the mass, so here it is an equilibrium state now, the mass is not moving. The mass is not moving. So you know that the weight is acting vertically downwards, mg. And the spring, the upper spring might have undergone extension, okay. So therefore that spring is trying to pull it up. So that is equal to K1 into delta ST1. Okay, the bottom spring might have compressed. So when you compress the spring, and what the spring tries to do, the spring tries to open up, and therefore the force from the bottom spring and is in the upward direction, and if K2 and if delta ST2 is the compression of the spring, in that case K1 into delta ST1 plus K2 into delta ST2 is equal to mg. I hope you got it. Okay, when I apply a force and that force is being shared, you can see here the force mg what I apply, and that force is being shared by the two. Okay, so therefore if you conclude just now at this stage itself, K1 and K2 are in parallel. When the force is shared in the arrangement by the two springs, they are always in parallel. So what will be the equivalent stiffness? What is the equivalent stiffness? That is equal to 1, it is K1 plus K2. So in that case, this is as good as if you have like this, you have a spring, single spring which is equal to K equivalent, which is equal to K1 plus K2, and you have a mass here. What is the stiffness of this? This is equal to omega n is equal to K1 plus K2. This is the equivalent stiffness divided by n. That is the natural frequency. You can straight away arrive at it. Okay, so with this I would like to close, but I feel I will take another 10 or 15 minutes in my next session. So on another two problems which I have it in mind. Okay, probably with that I shall also introduce you what is called as damped vibrations. Okay, those vibrations, damped vibrations, and our next discussion is going to be on that. We shall stop now. Have a good day.